Hi, David Vizard here, and you are watching PowerTech 10. If you can give me 10 or 20 minutes of your time, I will pass on many of the things that I've been able to learn in a career building high performance and race engines. Winning race engines, that is. Anyway, just give me that chance to show you what I can teach you, and I think you will find that you're well rewarded. Well, time's about up on this video. In part 2, I'm going to start with plug cables and a few things you should know about plug cables.
Right, okay, so now we know where I am. Right, so let's get started here. There's been a push for plug cables to have the minimum amount of resistance possible. That may sound good because the word resistance seems like it's contrary to what you might want. But in essence, no. If you're going to buy cheap cables, the most highly resistive but functional cables you can get are those carbon string ones. I mean, everybody has them. Axel have got a good line of those. They're yellow. Now, they'll work very well, but they don't last very long. Figure they'll be at peak performance for about a year at the most, and it depends on how much you use it. If it's a street rod that you're only going to drive out occasionally and you only do a few hundred miles a year, they could well last about 3 years. But after that, they begin to break down, mostly from environment under the hood. Now, let's consider the next best grade of plug wire here. Now, back in the day, before all these currently available fancy wires were the popular deal, standard procedure that I adopted was to use solid copper cable with 100 ohm or thereabouts resistor cap just before the plug. Now, this resistor helps suppress radio frequency emissions, and it did a reasonable job, but wasn't that spectacular. But it did generate a good spark. Now, I got this trick from my Professor Davis that I mentioned in part 1, the guy that was the advisor to the Ministry of Defense on weaponry, advanced weaponry. Anyway, so I followed that, and I can't say for sure whether we achieved much with it, because as a Mini got a bigger spark, so the results diminished. Now, I think at this point we were at our best spark for the job. Every time we went on the chassis dyno and connected up the fancy equipment, I'll remember the name of it, was Red, and they made chassis dynos, one of the first companies to do so. Every time we did that, our spark trace was always very good, and the chassis dyno setup guy commented on that a couple of times. He says, "Your engines always have a really clean spark, and we never see them this far." So obviously what I was doing was, at the time, realistically sensible. Now, we are talking about late 1960s here. Electronics has changed incredibly over that time. So, if any of you are electronics experts, send me your comments here, and I'll include them in part 3. But let me move on here. Next we have spiral wound cables. Now, I'm not sure who introduced these first. I've got a feeling that it was a Japanese company. There's 2 that are out there that are prominent. But anyway, what happens, instead of using resistance to dampen the RF frequencies generated by the spark, they used inductive cables. Now, these inductive cables act as a spring. It's about a mechanical thing for it. And as a result, they don't interfere with electronics as much or even at all. But they have almost no resistance. So, that is a good type of cable to use. Next point we need to look at on cables is, if we're going to use the mother and father of all ignition systems, one thing you will find apparent: the spark will break down the insulation. Standard stuff is 7 millimeters, right? Do yourself a favor, if you are using an MSD style ignition to its limit, you may want to consider using 8 millimeter cables, because there is a likelihood they will break down the insulation. Now, I've got on to MSD, and I should mention that the multi-spark deal doesn't work all the way up the RPM range. I forget where it stops multi-sparking. I think somewhere about 4,000 RPM it's doing 2 sparks. Now, is this system worthwhile? Well, I'd have to say on balance, yes. In terms of making horsepower, it's a proven entity, but it's certainly not the only one out there. Do I use MSD ignition? 70% of my ignition systems for dyno testing are in fact MSDs. And here's the thing, if you're just getting into the low key, shall we say, of hot rodding, the MSD6 does deliver, as do some of the others, right? Your cheapest way to go with a good spark, if you have an HEI ignition system, is to go with the MSD module that goes into the distributor. If you need a new distributor, give Performance Distributors a call. Telephone number's under here. They're very good. They build HEI distributors, custom ones. They're not overly expensive, but they are good. Try and avoid, where possible, buying any of these real cheap HEIs that are Asian knockoffs. I've experienced a couple of failures with those when testing them, and I've also had a lot of people say that they've had the distributors fail or have, you know, a major problem with fitting or something like that. So beware buying those. Now then, back to 8 millimeter spark plug cables. They are well worth the while. Keep them separated well. They need to be, if you're using a conventional ignition system and you're not trying to pump 60,000 volts through it, you can get away with a good 7 millimeter plug cable with about 1/8 of an inch gap between the two. And if you are using a plug design such as the one I showed in my design in part 1, you will find that the voltage at the cables is not necessarily reaching the levels consistent with the spark plug energy involved. So with my spark plug, and probably with an E3 spark plug, you can get a bigger spark for less voltage in the cables, so your cables should be better. Hope you understood all that. At this point, I want to move away from the actual spark generation and look at combustion characteristics, and then tie that in with the spark later on. First, let me contradict a commonly held belief that when a moment of ignition happens, the mixture explodes. No, it doesn't. When the spark passes through the gap between the electrodes of the plug, there's a delay time before the combustion really gets going, and it's called the delay time. Now, who'd have thought of that? It's only a short time, but we have a spark, boom. It lights a kernel of flame which for a moment doesn't go anywhere, and then whoosh, it goes off. Now, as for the mixture exploding, no way. An explosion is something that happens when combustion exceeds a certain speed. Now, dynamite burns at 2,000 miles an hour. I don't know what the threshold speed is to qualify it for an explosion. I think it's something like 1,000 miles an hour. But let me tell you, the mixture in the cylinder burns. It does not explode. At best, it's going at about 150 miles an hour across the combustion space. That's a long way from exploding. It needs to go about 6 times faster. Now, what does explode is detonation. That's when the combustion speed through the mixture is almost instant, because in that confined space we have consistent conditions, or relatively consistent conditions throughout, and the temperature of the charge goes up beyond the ignition point, and it does this more or less uniformly. So a flame front starts throughout the mixture at almost the same time, hence the knocking. Temperature is very high because the heat release rate is very high, and of course the pressure rise is almost instantaneous. There's a surefire definition of exploding: a near instantaneous pressure rise, a rate of pressure rise. Anyway, let's get back to combustion. A couple more of misnomers considering detonation. I've heard it said on plenty of occasions that the rattling from detonation is caused by 2 flame fronts colliding. That is absolutely BS, right? That is a misunderstanding of what's going on. Essentially, let me explain why this won't be so. Essentially, the flame front in the combustion is a change of state of the contents of the cylinder. In other words, here's the flame front, burnt gas is here, unburned gas is here, right? This flame front is not a solid thing. It is the front, the line on which the molecules of oxygen and gasoline change from being oxygen molecules and gasoline molecules to a combusted mixture, right, at high temperature. So although this flame front is going across, the molecules of air are not actually moving that much. They are moving because this front here, this combusted area, is at a higher pressure, so it's going to travel across the cylinder. We'll see that in one of the upcoming charts. But another thing is the way people talk about detonation. It sounds like we fully understand what's going on. We don't. I'm sure more is known about it now than it was a while back, but let me tell you, back in about 1970, I got to stay with the scientist slash engineer guy that figured out what happened to Apollo 13. Brilliant guy. He had a social problem, but his IQ was off the chart. And he talked about something concerning population 1 and population 2 molecules and atoms. Now, I kind of understood what he was saying 50 years ago, but I'm afraid my brain surgery has caused me to kind of lose track of what he meant. But nonetheless, it emphasizes the point that even people as brilliant as this guy was still hadn't come to a good conclusion as to what detonation exactly was. Now, if any of you have anything to add to what I'm saying, please let us know in the comments, because that'll be education for me as well as other viewers. Anyway, on to the combustion event. Here's the diagram we're going to be working with. What you're seeing here is a graph of the pressure rise and the amount by mass burned, that's the red line, versus the crank angle, which is along the bottom scale. The rectangles above the chart represent the combustion chamber at the various points marked on the chart. That is, the piston position will give the chamber shape or volume A, which is positioned on the graph at the point marked A and represents about 35 degrees. Top dead center is going to be around about position D. E follows that and F follows that. Now the part here that's very important is to look at the pressure rise and the volume burnt graph and see how at first they don't seem to make sense. Now that said, it will make a lot more sense in a moment. First, take a look at combustion chamber C. You'll note that the volume burned looks well over half of what's available. Based on what we see there, it looks like a lot of the charge has been burnt, but that's not the case. Check out point C on the thin line, which is the cylinder pressure, and you'll see that the pressure is rising. But if you check straight down on the bottom of the graph, that would be about 10 degrees before TDC, the combustion volume burned is only a couple of percent at the most. However, in C it looks like it's well over half. Now here's where we get this dilemma. If you look at the mass burned, it's not until we get to point D and then on up to E that the major amount gets consumed by the flame front. Now if you look at D and E combustion chambers, you'll see that the amount that's exhibited burning at D looks far more than the small amount shown by the red line. The red line showing about 10% burned, whereas the picture of what's going on in the cylinder looks like it's about 95% burned. The rising pressure of the burned part of the charge has pushed the unburned part of the charge into a smaller space. Now if you understood all that, it's going to make a lot of difference in how you'll see the importance of the ringland volume.
to the combustion process.
So you can see from that chart that the expanding gases push the unburned gases into a smaller space. So what appears to be a large volume burnt is a large volume, but the mass is not much, because now the unburned gases are trapped at high pressure in a smaller space. How is that relevant? Let's go and look at one of the areas of combustion efficiency that we need to take care of, and that is the top ringland volume. For those of you who might just be unaware of it, the piston diameter above the top ring is smaller than the diameter or the diameters that follow on down the piston. That's because the top gets hotter and they need to take care of the greater expansion there and the rocking and things like this. But almost all pistons have more clearance there than they actually need. Now, the further up you put the top ring, the more that volume decreases. When the combustion procedure starts, what happens is the parts of the ringland groove are the farthest they can be from the flame front. So what may only be about 1% of the volume of the entire charge when the piston's at bottom dead center gets to be a very noticeable volume proportionately when it gets to the top. Let's say we've got a 2 cc ringland volume and a 740 odd cc cylinder, as we would on a 350. So there's only 1/350th of it in the ringland. However, by the time we get to the top of the stroke, we have maybe 90 cc for a moderate compression ratio, right? But 2 cc in the ringland. And that means we now have 1/45th of the volume. But the pressure has gone up, and it actually turns out that we've got close to about 5% of the volume of fuel and air in the ringland. Well, it's quenched by the proximity of the bore wall and the piston, so it doesn't burn. So the further up we can put the ring, the better. And there have been ring designs which seek to eliminate the top ring altogether. Total Seal had one many years ago, but it resulted in a very heavy top ring, and this tended to get out of control at high RPM. Now let's look and see what difference it makes moving the ring up to cut that ringland volume. Now we can't move it up indefinitely because it starts to interfere with the valve cutout, but we can move it up a certain amount. And here's a chart showing the power difference.
Before going into details here, I would like to thank Ross Pistons for making 2 sets of pistons identical with the exception of the position of the top ring in relation to the top of the piston. If you look at the rows labelled in red, torque difference and horsepower difference, you will quickly see that setting the top ring about 75 thousandths nearer the top of the piston is worth quite a bit of torque and horsepower.
Well, it looks like I had more to say than I thought on this subject, and once again I've kind of reached a time limit here. I know I promised to show you how that difference in that spark plug deal, 10 times more spark value than we started off with in that preliminary picture. What I'm going to do now is show you where we ended up, the before and after, and in next edition I will show you how to do that really early on in the video so that I can stick to my promise of showing you the actual method of doing it. Anyway, thank you for tuning in here, and don't forget to like, subscribe, notify, share, and hit the thanks button with the $sign on it for St. Jude's. Thank you all for watching.